Alright guys, so today we are going to focus on the key schedule in AES, and that is because if I were to create the backdoor inside of the Intel CPU, I would focus on the key schedule, because the key schedule is the most effective place to put a backdoor, since it takes care of the key generation. So how does it work? Well, it looks a little bit like this. We have an input, and the input is a 128-bit encryption key. So in this example, we'll be using the following key. Two of these becomes 1 byte. So these right here, is the least significant byte. And what does the key schedule do? Well, it takes this 128-bit encryption key and creates. So from this encryption key, it creates 11 subkeys of the same length, 128-bit. So we are not, when we use AES, we are not using the encryption key to encrypt stuff, basically. We are using it to generate these subkeys, and we use those to encrypt stuff. So maybe you realize why it's an ideal place for a backdoor, because if the software that you're using is randomizing an encryption key and giving this to the CPU to create those subkeys, and the CPU might change these keys somehow, so it reduces the strength of the keys. So that is my idea anyway. And I'm going to prove this by creating my own C version of the AES key schedule algorithm. And I'm going to create an assembly version using this instruction in the CPU, and then compare the results, because they should differ if the backdoor is there. But first I need to show you how this key generation works. Let me just draw a couple of things. Alright, so the number to the left here, 1 to 11, these numbers, that is the subkey. And the subkey is divided into these 4 boxes, and each of these boxes is 32 bits in size. That makes a total of 44. That's basically how everything is built inside of this key schedule. All the components are 32 bits, and sometimes even less than that. So the numbers inside of the boxes, that is the index of that variable, so to speak. So the first thing we do, if you remember, we have this A, B, C, D, etc. Inside of the encryption key. So the first thing we do is we copy all of that into the first subkey. So the A goes here, and the B, and the C, and the D. How do we create the next line, the next subkey? Well, these 3 boxes right here to the right, we use one method, and for the leftmost box we use a different approach. And that's true for all of these. So it's quite simple with those three to the right. The only thing we do is we take this one and this one and we add those together. So basically we can say that this 5 index will be equal to the 0 index plus the 1 index. And this plus is an XOR operation. And then we do the same for these other boxes on the same level. So now we will have a value inside of these boxes depending on what the values in the previous subkey is. Alright, so that's easy enough. But how do we do with this leftmost box, the 4? Well, what we do is this. We take the value inside of this box right here. So the index just before the box we're interested in. So we go like this. And then we take the value inside of this one. So those two together we add and put inside of this. But we do one more thing, and that's this thing right here. This is what I call the G function. So before we add those values together, we pass this 3 value right here inside of this G function. So if I were to write this like I did right here, the 4 box will be equal to the 0 box plus the G function of 3. Okay, and this is all that is done. This same thing goes for the 3rd subkey and the 4th all the way up to 11. What's inside of this G function? Well, the G function works like this. And I can mention that universities usually call this the G function to differentiate from the F function, which is inside of the DES encryptions. But if you read the original proposal for this AES cipher, which is called Rheindal, then it's called the F function. But this is the only function there is, so it doesn't really matter what we call it. And this G function, it has an input and an output. And as you might imagine, both of these are 32-bit values. And what we do is we split up these 32 bits into 4 boxes of 8 bits, so 1 byte each. So it looks a little bit something like this. So this is index 0 and 1 and 2 and 3. And each of these boxes are 1 byte each, or 8 bits. And we do 3 different operations on these values. So let's say we have 6, 7, 8, and 9, just as an example. First thing we do is a rotation. It will look a little bit like this. So remember the indices. Here we have 1 and 2 and 3, and now we have 0 right here. So what has happened is we have moved this whole array of numbers one step to the right, and we have taken this and moved it there to the rightmost position. So it's like a cyclic shift. So that is the first operation. And let's also fill in the numbers just to make this very clear, like so. Okay, so that's step number 1. The next step is we do substitutions. So what is a substitution? Well, basically we have a big table which is called an S box table. And this table says that if we go in with the value 7, we go out with some other value. I don't have it in my brain right now, but let's say, because there are 256 different, but let's say 7 will turn into a 15, and the 8 will become, I don't know, AF. The 6 will be CC, and the what do we have left? 6, 7, 8, 9 might be something like, I don't know, 0, 1 perhaps. So it's just a table where if we go in with a specific value, we go out with another value. And this happens for each of these bytes. And that is the second out of 3 different operations inside of the G function. And the last thing is we don't do anything more with these 3. These are, so let's see, 6, 7, and 9. So for this and these 2, we have the result value right here. But for this leftmost box, the 8 in this case, we do one more thing. We add something which is called the round constant. So it will look a little bit like this. So the same way we added with an XOR before, we take this round constant and we add, in this case, the value AF, and we get something out, and then we assemble all of these numbers, and that is the output, that is the return value of this G function. So it's a couple of steps, but it's not very advanced stuff. Each step is not very advanced on its own. Well, it's a lot to look at in a sketch like this, but it's not really very difficult to understand. But what about these round constants? What are these? Depending on what round we're in, so basically if we're creating the first subkey or the second or the 11th, we use different round constants. So the first one is 1, and then we have 2 and 4, 8, 16, 32. So it keeps increasing. 1, 2, 3, 4, 5, 6. Then we have 64, 128. And then we have 2 more values, which I don't remember right now. But they are not the double value like this. They differ. So the last 2 rounds, there is something like EF and something like that. And we just add those constants based on the rounds. Okay, so this is how the AES key schedule is supposed to work according to the specification. But is this how it works inside of the CPU? Well, I have analyzed this, read a lot of documentation, tested a lot of different values, and this is what happens inside of the CPU when you tell it to create subkeys out of one input key. So let's say we have the same input key. What it does in pseudocode is we have the following things. So we have 2 so-called input and output registers. So these are like the parameters and the return values if we were to compare it to like C or something. And these are 128 bits. So when we execute this function call, so to speak, and the function call's name is AES key gen assist. So it takes one 128-bit input value, and it produces one 128 bits subkey. And you execute this 11 times. And it also takes an input with a round constant. So you need to specify that as well. And it does also use what the documentation is calling X registers. And that is like a temporary variable, 32 bits each, and there are 4 of these. Okay, so what happens? The first thing is we set x0 equal to the input, and we take the first 32, so 0 to 31 indices. Since we start with 0, we go to 127. Okay, so now we have those integer values, those 32-bit values that this uses as well. If you remember, each of these boxes are 32-bit each. And then we follow the same schedule basically. So what we do with these values is we do rotation, XOR, and we do one more thing, and that is adding of the round constants. And that's it. And the interesting thing is which of these temporary variables we use. We use x0, and we does two different operations on x0. And we use x2, and we do two different operations on x2. And then we assemble an output based on that. So we don't use x1 at all. We don't use x3 at all. We only use two of these intermediary variables. And as you also see, we have skipped one step, and that is those substitution boxes. And what does that mean? Well, the substitution boxes are there, so we will be nonlinear. Because if we are linear, then we can set up a couple of different equations and solve these equations in order to find the key. And that we don't want that, so that's why AES has these S boxes. But we don't use those inside of the CPU. And we only use half of the key. So since we are only using the x0 and x2 registers, that means that we are using this part of the key. So we are not using these B's, we are not using these D's, which means that we turn this into a 64-bit cipher. And there's a huge difference between 128 and 64, as you know if you saw the last episode. 64 is possible to crack with a home computer basically nowadays, almost at least. But 128 bits is you'd have to crack as many combinations as there are like molecules or atoms in the known universe. So that's completely out of reach. But 64-bit is definitely within range, especially for government agencies. And especially if we have reduced the nonlinearity or removed it by removing those S boxes. So this is my findings, and the rest of this episode I want to show you how I figured this stuff out. I'm going to show you how to code all of these AES key schedule algorithms using assembly with these with this AES keygen syst instruction, and how to code the rest of the C program we started last week when a software implementation of the key schedule. And then we will try a couple of values of input keys and see what the results we get out, and compare the two implementations. And we will also look a little bit inside of the manual for these hardware accelerated instructions. And I will show you exactly how these X registers and these things, these instructions work on them. So let's get started. Sup guys, welcome to today's show. So today we are going to finish our C implementation of the AES key schedule, and we will also create an assembly implementation, which will be very simple to do actually, since everything is integrated into the actual CPU. And we will be hunting for the CPU backdoor, which I believe might be there. And today we'll be attacking the key schedule. So by the end of this episode, we will hopefully know if it's hidden inside of the key schedule, which would be a perfect place for it to be actually. Alright, if you remember, like last time, we prepared the utility functions and created all the data types for our implementation. And that's about as far as we got. Today we are going to create the actual key generation function according to these formulas, and the only tricky part, I think, will be this G function, which will use the AES S boxes and whatnot. But more about that bridge when we come there. For now, I am only going to define this G function as an identity function for the time being, so it will return itself. So let's see, the G function is going to return a word, and a word in the AES for words is just a regular 32-bit integer. So we'll have a word with a G function which takes an input word. So word input, and it's going to take the round, because we are going to create 11 subkeys, and so there are 11 so-called rounds, and depending on the round, this input will be handled differently, so we need to pass it to the actual function. So we'll have an int8 round, and for now we will only return the input like so. So the round for now at least will be unused, and I define it like this. So now we only need to create the generate function, generate keys. So it will take an input key, the 128-bit AES key, the encryption key, and from that key it will generate 11 subkeys of the same length, 128 bits per key. So this will be a pointer to an array. Okay, let's see if we can get this done. So we will have, let me just see. We will have word and the gen keys function, which will take one word as an input, and this will be the let's just call it key, because it's the main encryption key of 128 bits. So, what do we need to work with? We need a key array. Did I specify that? Yeah, I call it word array. So that's the 44 integers. Because the 11 subkeys are 128 bits each, and if we divide that into words, that would be 44 integers. So we'll have a word array. Let's call it W according to the standard. Let's see what else we need. We need a couple of intermediary or temporary variables. So let's say we'll do word X, Y, Z, something like that. And we also need to keep track of the counter. So I think we can do int 8, I, and J. All right, so let's start by zeroing out the word array. So we pass it to the 0, and we cast it into 8 bits integers. So let's see, we will pass it the W, and this will be size, let's do it like this, size of word times 44. Or let's see, yeah, that'll be good. Okay, so what's next? Well, we need to zero initialize. Our I will be equal to J will be equal to 0. So both of these will be 0. Or it's better to do it inside of the 4, I think. It shows our intent a little bit better. So let's see, before we start, we need to copy the AES key into the first 4 words. So I think the easiest way will be to create a pointer. Let's see. What if we were to do something like this? If we create a void, V for void, and we create our word-sized word pointer, and we point our void pointer against the beginning of the word array. So void star W, and now we should be able to point our word pointer to the void pointer, basically. And why we need to jump through these hoops with a void star, that's has to do with how GCC enforces typecasting. It used to be more free, but not any longer. Okay, so now we should be able to, let's see.
should be able to, maybe the easiest way is just to do something like we set the word pointer, so this is the first word of the 44 word array, and that should be equal to the first part of the key. So something like word star address of the key. Let's see. Maybe we can do, let's do a V1 and V2. Maybe we'd make it a little bit more complicated than we need to, but at least it will work. So we have one word pointer and a second one. So let's see. V1 will be equal to this, and the word pointer 1 will be equal to V1. So this is the input, output I mean. And for the input we do the same. So we set our V2 equal to void star key. And our second word pointer will be equal to word star V2. So this should be equal to and now we don't need to cast it any longer, I think. So we're prompt, yeah, we need to do this instead. So this should be, no we don't. So word pointer 1, word pointer 2 should be equal to word pointer 1. And then we need to increase this and increase this. And then we do this 4 times. 1 for each integer-sized part of the input key. Yeah, I think this will work. Let's double check before we go on so we don't mess this up from the beginning. We can use the print hex from Birch utils, and we will, let's see, in order to, no, we can do this. So let's see, what do we want to print? We want to print our first 4 bytes, no, our first 4 ints of the array. So we pass it the W, and we want to show, let's see, well, 128 bits divided by 8. This needs to be cast into a 16, like so, And then let's just return 0 for now. Let's see. We can clean out all of this, and we create a key-sized. Let's see. I think we made a mistake. No, this is key-sized. So we need to change this. And let's call the key K instead. So now we can create a key. Let's call it K. And let's say K is equal to, I don't know, a very large number. So this will be, this is 1 byte. So 8, 16, 32. So 32, 64, 128. So now we have an input key, and it will, we don't care about the return value at this point. So generate keys, and we give it a K, and now it should hopefully print the output. We need to give it something that divides the different characters. Let's say a colon. All right. So we make clean, and we make, I forgot to comment this out. We need to have 0x here, and not here. Redefinition of G. Did I already? This should be a J, not an I. And now I believe it will compile. And it complains it's too big for its type, but it always seems to complain and work anyway when it comes to that. So let's see. Maybe we should print the input as well, so we can check the difference. So here we will have the K like this, I suppose. So the input uses spaces and the output uses colon as a separator. Okay. Let's make this a little bit easier. We set this to something of an integer size. So 1, 2, 3, 4, and we times it by 4. Okay. Still 0. Maybe we shouldn't have this. It's weird that the input becomes 0. What if we were to print, let's say, the first integer bit of this? So 0x, like dot 8. X. And then we do word. Okay. Okay, so here we do get the value, but when we pass it to the function, it kind of disappears. Let's see, V2 is the key. I think we mixed these around. This should probably be like so, and this like so. Now I think it'll work. Alright, seems to be the same. But I want to try it with something that doesn't contain all these zeros. Because how did we define key? Key is an int 128. And this, how does our make file look? C23 should work. Let's set it to the maximum and see what happens. And the maximum is usually like this. Okay. It seems it's been copied the way we want it to. That's good. But I want to have something which is more different. Let's generate the key this way instead. We create 128 and a P and int16 size. The size will be the size of well, it will be 128 divided by 8. So that's the number of bytes. And let's make a short loop. We set I equal to 0 as long as I is less than the size, I plus plus. And we set P equal to our key. And at each iteration, we increase our P. And we set P equal to I. Let's see what we get. Let's make this an int 8 instead, so we don't need to cast. Let's see, I set to 0, P will be set to, maybe we need to do this. Okay, that looks better. So now we have a key which is consisting of a lot of different numbers. So our copy function worked. Now we can begin our key generation. So let's uncomment this so I get a little bit of colors. And let me just take a sip of water and we will begin this. Alright, so what we have done this far works. Let's remove this and let's start our key generation. So we are going to have a loop where we go from I is equal to, let's see, this should go from 1 to 44, I guess, or from 0 to 43 maybe. Let me just consult my manual for the AES, algorithm. So let's see. Yes, per key, I will go from 1 to 10. So I guess we could I think 0 to 43 is the easiest way, since we will be dealing with the whole array at once. So we set this to 0 as long as I is less than 44. We increase I. So we will do two different things depending on if we are okay. I think we can do it like this anyway. So depending if we are dealing with the first thing, the first word of the array, we will use this first formula. And for the three other parts of the subkey, we will use the second, easier thing. So let's see. we can set our first intermediary value. So we need to grab this, and then we need to grab this, put it into the G function, and then we just XOR these together. So X will be equal to, let's see, 4 times I minus 1. We need to have something for the index as well. Let's zero initialize all of these. So X will be equal to Y, which will be equal to Z, which will be equal to IDX, which will all be equal to 0. So now we can take the index and calculate this. So I minus 1 times 4. That's our index. And then we can grab our intermediate value by taking this from the array. Then we do similar with the second thing. So we set the IDX equal to this time it will be 4 times I minus 1, like this. And then we have our Y, which will be equal to W of this index. So now we have this value. And this needs to be passed through the G function. Maybe we can do it like this. So we take our third intermediate value, that's our Z, and this will be equal to our X XOR the G of Y. So now the Z contains all of this, and now we need to put it here. So we calculate our index as 4 times I, and then we set the W of index to Z. And now we have handled all of this. Mm, mm, mm. And then I guess we could do it like this, so we don't need to have an additional loop around this. However, we do need to have an additional loop around this. So let's do 4j is equal to 1, and we check if j is less than, so this should be 1, 2, and 3, so it should be less than 4, and j plus plus. So now is the second formula, but we will do it pretty much the same by starting to define the index as this. So the index will be equal to 4 times I plus j minus 1. And from there we grab the x, like so. And then we do the same for the other one. The index will be, in this case, 4 times I minus 1 plus j. And this will be our y, which will be equal to w at that index. Alright, and now we just XOR these together. So our index is going to be equal to 4 times I plus j. Our c will be equal to x XOR to y. And w at this index is equal to z. Alright, I think that's basically it actually. Let's copy this stuff back to the beginning. And do this. So now we need to return this whole array, and we can't return a word array, so we need to malloc this thing as this. So let's create, we can reuse our word pointer actually. So let's say our word pointer 1 is equal, now we need to calculate the size first. Do we have a size variable? We don't. So int 16 size. And the size is going to be equal to, let's see, we need 44 words. So size of word times 44. Now we can set our word pointer 1 equal to malloc of size. And we can zero out this thing. So we need to cast it like this. And the size is size. Let's also assert that we do have a word pointer 1, so not the malloc will fail. And now we just need to copy our whole array into this output variable. So we copy into Let's see. To our word pointer 1, that's our destination. Our source is the W itself, and we are copying size bytes. And this should be done outside of the loop. And now we can just return our word pointer 1. So let's see what we got. We have our key. We need an output, so let's say word subkeys. I wonder if it's the right thing to use word size here. Because we want this to be keys, actually. But it's easy enough to cast that thing anyway, so let's not mind at this point. So subkeys will be equal to this. If we don't have a subkeys, we return an error. Subkey generation failed. And we return -1. But if we do have an output, we want to print this like we did before. So we print hex, and we need to cast this into an int8 subkeys. And how many bytes? That's 128 divided by 8. And we don't need to use a separator at this point. And then we can free our subkeys and return. All right, so now we're done with this. Let's see if it compiles. It will probably require a little bit of troubleshooting, I suppose. Too few arguments to G, that's correct. We need to keep track of what round we are in. That's right. So let's see how to figure that out. it's going to be every 11th. Let's see. So why did I want this to go from 1 to 10? Because there's 10 subkeys. So the round, if we set this to 10, or like this, let's see, less than 11. So it goes from 1 to 10. Then I is the round. Remove this. And to the G function, we can pass the I, which is the round. But we want to create 11 subkeys. So this should be like this, I suppose. 1 to 11. And for each subkey, we will do this for the first word-sized chunk, and this for the remaining 3. Which means this whole thing will generate 1 subkey per round. Okay, that makes sense. I think we don't need to change much else, actually. Okay, this was just a typo. Iteration 10 invokes undefined behavior. That's right, the first 4, so the first subkey we have already handled here, because the first subkey is equal to the input key, which means this should have been like this. So, and this will be 4 times 1 at the first iteration, which means we are doing it correctly. Okay, it's compiled without any errors, without any warnings. That's a good sign, no? So let's see what our all of our subkeys is gonna be. No, we just printed the first one, but it looks kinda alright, doesn't it? And if we want to print all of them, we could do something like 4i is equal to let's go from 1 to 12. I++, and we will also set p equal to word, no, p equal to subkeys. And at each iteration, we increase p by 1 subkey. And then we can replace this by p. And I believe this will work. Got disconnected. My internet service provider quite often reboots the switches during the night. So that's a little bit annoying. Let's take a short break until it's working again. Alright, so now I believe that my internet connection should be back. Let's see. Yes, it is. Okay, this was the wrong one. Let's see, go to Intel 32. And it's this, I think. Yeah. Alright, so we make clean, jump down a little bit, clear the screen, and run make. Oh, compiled without warnings. I like that. Let's see what happens. Okay, it didn't update my code because I had no internet connection. So let's just do this and we save. And we try again. Huh? Maybe we got disconnected. Yes, we did. And we did get disconnected from the VPN as well, as it seems. Let's try again. All right. And the nice thing is, now that we are connected again, it's synced up. So the only thing we need to do is save, and no problem. There we go. Okay, so from this input key, the AES key scheduling algorithm has generated those 10 additional subkeys. But how do we know that this works? Well, we need to verify it somehow without having to rely on something which is backdoored. So we need to find some other AES scheduling algorithm implementation and just verify that we got the same as they did. But before we can do that, we need to take care of this little G function, right? Because at the moment we are not caring too much about it, which basically means that 1, 2, 1, 2, 1, 2, 1, 2. This part of the key is wrong. This part should be correct, I think. Because this first 32 bits is what we passed into the G function. The rest is unaffected. So basically we could try to use another key scheduling implementation and see if it generates this part. Maybe we should do that. There must be some online tooling for this, right? Something like, I don't know, online AS key scheduling. But I don't want to have something that explains it. I want something that I can test. Maybe we can test. Here we go, I think. But this is some code. Pi, main pi, and we give it this. Okay. But it does not look even remotely the same. Maybe we should finish the G function. I guess it, oh yeah, of course. It will influence the rest, even though only this is affected. Because this makes use of this as input. So, alright, let's finish the code first and then we try it against this, okay? We can attach here, and we go to this screen again. And we were at TMP key schedule. We set it to our home. And now we'll try to create this G function, which is a bit tricky, I think, but we will figure it out together. Alright, so first of all, we need to, let's see, to the G function we pass one word, right? Yes. So that word should be converted into bytes. And that's why we have these subword to word functions that we created last time. So let's begin there. We will need to have something of subword size. So subword, and that should be equal to word to subword, and we give it the input. Maybe we can get better names here. Let's say this is the word and this is the round. And if we don't, we can even assert that we get this back actually. Okay, so this is an array of 4 bytes, and we need to rearrange this a bit. So let's see. Let's create a subword which is not a pointer. Let's just call this S of size 4. Right? So let's see. Let me just check my AES reference. So what we should do is, right, we should shift everything to the left byte-wise. So basically we can do like this. S0 will be equal to SW1. And 1 will be equal to 2. 2 will be equal to 3. And 3 will be equal to 0. I think that's correct. Let's see. So the last one, let's see, the first one should be equal to the 1, 2, 3, 0. All right, so that's correct. The next step is we push all of these through a substitution box, an S box. And most encryption schemes have one. That's basically a long list of numbers, usually like 256. So if input is this, then output is that. It's just a regular 1-byte substitution. So we can make it easier for ourselves if we define a couple of intermediate structures. So we have S, and we get a T, and perhaps we even need an STU as well. So our T0 should be equal to our S0, but we put it into an S box. Which means we need to define a new function. And this is word, this is byte, byte-sized. So we have an int8 S box, and we have an int8 input. So int8 S box, int8 byte. Alright, so we need to either calculate the AES S box, which basically are inverses for so-called Galois fields, 2 to the 8th. But I don't know if there are C functions for that. Maybe it's inside of math.h or something. Galois fields C math.h. Maybe we should say libmath instead. No, it seems we either need to use some other library for calculating Galois fields or creating our own, and that's a bit too much, I think. So maybe we should just grab the S box, and because it's always the same, so we can, if we get our hands on the AES S box, we can use it in our code. So let's see, AES S box, and hopefully we can get it in some format that we can use easily. So this is it. So basically, if we have the number, I don't know, 0 to 20 in hex, then it will return 90. No, that's not correct. Let's see. This will be 22. So if we have the hexadecimal 22 as an input, the output will be a hexadecimal 93. And that holds for all of these, even for 00, 0. So let's see. I am tempted to break my no copy rule, my NOPI rule, but I don't want to do that. And since the NOPI rule only applies to code, there's nothing that says that we can't copy this thing and use it somehow. Let's see, how does it look if we just paste it into some file as box.txt? Not super great. But maybe we can still use it. If we were to, we need to remove this first thing because this is just the headline or whatever. So 3x like so. And we remove the first line. Say this. So how does it look now? All right. And now we want to remove everything which is not a number. So if we do something like Z-E and we search for characters 0 to 9, A to F, and everything which is not this should be substituted to nothing. And the input is SBox K. Maybe we should still have some separator. Ah, now we're talking. Okay, so now we have it in a good enough format. How do we get it into our C file in an easy enough kind of way? Maybe we can do some more. Let's create a temporary directory, move it there. And this will be our A. So then we do some more sad magic. Let's see, we want to search for a space. And we want to replace that space with 0x. No, we can do this. We're going to replace it by a comma. a space, and 0x. Okay, now we got everything but the first thing. So we want to do another substitution where we find the beginning of the line. And there we want to put, let's see, zero x. Okay, that didn't work. Oh, I'm doing the end of the line. This should be beginning of the line. Alright, that's good. And for the end of the line, we want to replace with a comma. So now we need to change this to this, and a comma, G, and we're at C, and go to D. Okay, this we can work with. So if we now go to this, then we do something like int 8 AES SBox is equal to this, and then at the end we do that and this. Then we copy this thing, we go to our C file, paste it in, and let's jump out like so. It's a little bit annoying that it puts 2 lines at each, but I think we can look past that. So this makes our SBox function very simple, because the only thing we need to return is the AES SBox at position byte. And let's test it first and foremost. So let's just do printf 0x percent dot 02 x. So this means we want it in hexadecimal and 2 digits. Then we should also tell it to be LL. No, not LL. What happened now? HHX. That means it's a byte. So we do SBox and let's say 0x AB. And then we exit 1. Alright, and if we go to this thing here, and what did we say? AB. So we look up A, that's here, this line, and A, B is this. 62. So if we get 62 back, we know our SBox works. All right? Why did it do this? 102 KSC. Right, we changed the input to W, like this. And we haven't returned anything, we need to do something at least for now. All right, so what did I say? A, B, 62. All right, the SBox works. That's great. All right, so back to this thing then. So now we have done the second step of the 3-step thing inside of the G function. And now there's only one thing left, that we need to change this first byte of the T. But we need to do some calculations in Galois fields again. So we need to create one more function, which is the round constant. So we will have an int 8 and it'll be a round const and it'll take an int 8. So int 8 round const int 8 input. And here we need to do some stuff. And I found some PDF about this, which defines it like this. So this is how we calculate what the round constant is. And then we need to we need to do times of this thing as a polynomial. Well, well. Let's start by creating those round constants. That looks simple enough, at least. So we need to tell it what round it is. Let's do, this is a byte, this is a round. So when we call this thing, we need to pass it the current round. So let's see. Let's create this array of round constants. And these are from 1 to 11. So let's do 12 here, doesn't matter. And RC1 should be equal to 1. Then we have a for loop where we set x equal to 2. And as long as x is less than 12, we do x plus plus. Each position, we need an index. The index should be equal to j minus 1. So in our case, it will be x minus 1. And RC of x will be equal to 2 times the last one. So RC of index And now we can return RC of current round. So let's assert that R is more than 0 and that R is less than 12. And now as the last step, we will do U0 equal to T0. So it will be the same as in the last step, only we will, in this place, take the round constant of the current round and add that to this, I think. Or should we XOR it? I think we can XOR it, but I'm not entirely sure. Let's see what we end up with. And then we need to return this as a word. So we need to use our subword to word function. Subword to word. And this should be a subword star of U. I wonder if we can do that conversion, but I think we should be able to. Yeah, I think so. Let's see what happens. It's 107. Yes. Too few arguments. We change the signature. what function? rconst. rconst int 8b int 8r. Did we get disconnected again? No. Ah, wait. Right. We need to give the correct argument as well. But we never use that actually. Do we? Don't think so. So let's just remove this. And this. Try again. Okay, 135. Subword to word it should be. Okay, it compiles. Oh, we need to change this back here. Let's remove this stuff and moment of truth, ladies and gentlemen. Will our implementation work? All right, we do get something. All right, let's try this out. There we go.
But this will be all for today. If you like this episode, please like and subscribe, and we will continue this project in a later episode. Thanks for watching. Thanks for today.